Great. Welcome, everyone. Good morning, good afternoon, good evening. My name is David Koick, and I'm the Chief Scientist of Ocean Visions. Thank you for joining our webinar today. This is part of Ocean Vision's webinar series to highlight solutions at the Ocean Climate Nexus. And today, we're really thrilled to welcome our colleagues from ARPA-E today to talk about their new sensor program. Today's webinar is called An Upcoming ARPA-E Program on Marine CO2 Removal, Measurement, Reporting, and Validation Technology Development. CO2, Sensing Export of Anthropogenic Carbon Through Ocean Observation. For those of you who don't know, the Advanced Research Projects Agency for Energy, or ARPA-E, is part of the US Department of Energy dedicated to funding high-risk, high-reward, and potentially disruptive technology in the energy and emissions mitigation space. ARPA-E is intending to announce a $30 to $50 million three-year federally funded program that seeks to develop new sensor technology for the scaled quantification of carbon fluxes. The purpose of this program is to create novel sensor and modeling technologies that allow us to quantitatively value potential marine CO2 removal approaches, such as ocean iron fertilization, ocean alkalinity enhancement, seaweed sinking, and ecosystem restoration, among others. Present-day technology is insufficient in assessing these removal rates and fates due to the lack of spatial coverage, sensor endurance, and cost. And this program aims to overcome these challenges. So it's a real thrill to welcome Dr. Simon Freeman and Dan Rogers here to talk about this program, and I want to introduce these panelists for a second. Dr. Simon Freeman serves as the Program Director at the Advanced Research Projects Agency, Energy. His focus at ARPA-E is on maritime energy and environmental sensing technologies. Dr. Freeman previously worked as a civilian oceanographer for the US Naval Research Laboratory and the Naval Undersea Warfare Center Division in Newport. Dr. Freeman was the principal investigator in the development of inflatable and bio-inspired soft robotic systems for underwater vehicle and sensor design, new signal processing methods for acoustic sensing, detection, and environmental exploitation, and pressure-tolerant technologies to enhance our access to the seabed. Dr. Freeman earned his bachelor's with honors in mechanical engineering and a bachelor's in marine science from the University of Auckland in New Zealand, and a PhD in oceanography from the Scripps Institution of Oceanography. Dan Rogers serves as the Tech to Market Advisor at ARPA-E, where he focuses on transformative, high-impact marine technologies to address our society's most pressing ocean-related energy and critical resource needs. Dan brings an extensive background in underwater technology operation, engineering, business development, and strategic partnership building in the marine science and technology fields. Dan has supported dozens of deep-sea robotic missions across the globe as a remotely operated vehicle pilot and mechanical engineer, and served as the technical lead on many of these missions. In his previous position at the Washington, D.C.-based Consortium for Ocean Leadership, Dan organized and facilitated workshops and strategic convenings involving dozens of partners from across industry, government, and academic institutions to capitalize on shared priorities and advance community-wide goals for ocean science, data, and technology. Dan holds a bachelor's in physics from the University of Massachusetts and a master's from the University of Hawaii. Additionally, he holds an MBA with a concentration in environmental policy from the University of Massachusetts, Dartmouth. So welcome, Dan and Simon. Before we get started, and before I turn over the mic to you two, I just want to let everybody know a few logistics. We're going to have Dan and Simon speak for about 40 minutes, and then there's going to be a Q&A afterwards. And so please put your questions in the chat. We'll monitor that chat, and then we'll use that to help start the Q&A at the end of Dan and Simon's presentation. And just a reminder to please keep yourself on mute to decrease background noise. So without further ado, I'd like to turn it over to Simon and Dan, and thanks for joining us today.
Thanks so much, Dave. And thank you also for the opportunity to present to the community here. And we're really excited about what we hope to achieve through this program at ARPA-E. So I'll begin this presentation just to clarify by clarifying a few things. We're going to use two acronyms, CDR for carbon dioxide removal and MRV for measurement, reporting, and validation. So we use those quite a lot throughout the presentation. Now, before I begin, I just want to talk a little about what ARPA-E is, or who we are. we are a government federal funding agency. We fund high risk, potentially high reward technology development related to energy, and that includes emissions mitigation. So solutions to climate change problems is within scope. As Dave mentioned, we're part of the Department of Energy, but the model for ARPA-E was developed after the successful DARPA agency, so Defense Advanced Research Projects Agency, and their ideas for rapidly innovating and trying high risk, potentially high reward research projects. So next slide, please. Just a little bit of history. ARPA-E was formed in 2007. We were first funded in 2009. And as of, that should say 2022, we have more than 1,300 awards and 66 programs. We have an annual budget of around $450 million to spend on high impact R&D. Next slide, please. So very quickly, our mission areas encompass 5 broad regions in the energy landscape here. Some of them are not too relevant to what we're talking about today. For example, the cleanup of radioactive waste, but reducing emissions is central to our motivations here, and also improving efficiency. So we are convinced that by 2050, the negative carbon industry will be one of the biggest on the planet. And how do we make that more efficient? Because we're going to need a lot of energy to capture CO2. Next slide, please. So just want to talk a little bit about the overall motivation for CCO2. So there's a plot on the left here. This is something that you may be familiar with. It's a figure from the UN Environmental Program published in 2017, and it shows the track that we need to take in emissions reduction to maintain global warming to or below 2 degrees Celsius. So rather optimistically, around the 2020 timeframe, they imagined a dramatic decrease in the rate of CO2 emissions or CO2 emission equivalent emissions. And you can see on the track, on the horizontal axis, you've got time stretching out to 2100. On the vertical axis, that's equivalent gigatons of greenhouse gas emissions per year. And so to stay below 2 degrees Celsius, they estimated that a significant amount of effort would need to be expended in developing conventional abatement technologies. Those are things like wind, solar, and nuclear, capturing emissions, such as by installing scrubbers on diesel engines, etc. But also this blue area underneath, the negative removal industry, or the negative emissions industry. And we've added a few sort of approximate cartoons here to suggest that since that time, since 2017, business as usual has actually been worse than predicted. So that negative emissions industry is going to have to be much bigger than predicted initially. And the initial scales were on the order of 10 gigatons per year by 2050 and 20 gigatons by 2100. But we think it's going to be more than that. The other question here too is, where is that carbon going to be stored? And you can see on the right, there's a picture of the Earth that is to scale from the viewpoint of the Cook Islands. Most of the planet is covered by the ocean. So we think it's only logical that most of this carbon is sequestered at sea. Next slide, please. And case in point, this table is a summary of information provided by the National Academy's report on negative emissions technology and reliable sequestration that was issued in 2019. They looked at terrestrial and coastal blue carbon dioxide removal technologies and found that maximum safe limits were between 9 and 11 gigatons per year, which is a lot less than 20. And we also have concerns about whether or not this sequestration will be permanent. For example, if you plant a forest for afforestation, in 50 years' time, we're not really sure if that forest will still be there due to forest fires or changes in land use, etc. Next slide, please. Conversely, the ocean is a much, much larger repository of carbon. This is a somewhat dated figure from the IPCC, but the numbers are still relevant. Those numbers represent gigatons of carbon per year. So the yellow arrows represent fluxes. So roughly 100 gigatons of carbon moves in and out of the ocean, surface ocean per year. 38,100 gigatons of carbon is stored in the deep ocean. So these blue boxes represent storage. If we were to take all the anthropogenically produced CO2 over the last 200 years and put that in the ocean somehow, that would only represent an increase of about 1% in the amount of CO2, the amount of carbon stored at sea. So it's truly an enormous system, and even small shifts in carbon dioxide fluxes in the ocean would represent significant consequences to atmospheric CO2 concentrations. Next slide, please. So there are ideas and efforts in existence today regarding the development of carbon dioxide removal technologies. And I'm not really going to talk about them today, but if you are interested, there's a pretty good report issued by the National Academy of Sciences in December 2021 called Ocean-Based Carbon Dioxide Removal, a research strategy agenda. So I direct you to that publication. It's available for free online, but they broadly talk about these 6 methods of CDR. And if you go to the next slide, please. While these techniques are potentially feasible, there are significant unknowns regarding each of them. And most of those unknowns relate to the efficacy. How effective would it be to do these things at scale? How much carbon would we actually draw down, and for how long out of the atmosphere? So the next slide, please. So to address some of those concerns, ARPA-E is going to launch a $30 to $50 million program on marine carbon dioxide sensor technology development. So in that stylized image on the right of the slide, you see what we think is what the CO2 removal industry will look like in the future. So let's say you have some hypothetical ocean CDR device. It captures carbon from the surface oceans and atmosphere. You can then sell carbon offset credits to legacy emissions industries, such as steel making or very difficult to decarbonize industries. And they would in turn pay for those carbon credits. Measurement, reporting, and validation is the quantification of how effective your ocean CDR process is. You can see that's represented by those 2 autonomous underwater vehicles sensing particles in the water. That dashed box represents the program scope of ARPA-E's program. We want to try to create viable measurement, reporting, and validation technologies for MCDR. We want to do that through 2 technical thrusts. Number 1, we want to develop wave-based scalable carbon sensing technology. And by wave-based, I mean there's an emphasis on electromagnetic, optical, acoustic techniques. These would potentially enable the volumetric quantification of carbon parameters in seawater. The second technical area is to create effective models to estimate CDR performance. So these models will rely on these new comprehensive volumetric data sets. They'll be specific to certain CDR applications that are regionally focused. We think that this is really important because quantification of marine CDR gives this industry financial value in a carbon market. And we're going to need to do this very quickly because we need to rapidly scale for solutions to reverse the climate disaster. We have to stay below 2 degrees Celsius of global warming. And lastly, we think that the oceans offer substantial scaling possibilities for multi-gigaton scale MCDR. Next slide, please. So I should just clarify, there's a lot of interest in CDR at the moment, and we are not running a CDR program here, despite what it sounds like. There's perhaps $1 billion worth of philanthropic money, venture capital funding, funding from other government agencies, including other groups in the DOE, that seeks to understand and develop and trial ocean CDR. We are specifically going after the MRV challenges, and they're very difficult. It's sort of like tracking a plume of smoke after it's left a chimney for 6 months. It's a very challenging problem, but we think it's a necessary component for this future marine CO2 removal industry. Next slide, please. So very quick overview about the ocean parameters that we think are relevant to MRV. In the upper center of this slide, you have the inorganic carbon equilibrium reaction there. CO2 is dissolved in seawater, and then it dissociates into carboxylic acid, bicarbonate and carbonate, and there's a tie to pH in that reaction. So quantifying these parameters is important. But there are some other very important parameters too that we are interested in trying to quantify as well, including dissolved organic carbon. So the dissolved organic carbon pool is the second largest pool of carbon in the ocean. The particulate organic carbon that rains down from surface productivity. There's a picture of marine snow there on the right. And that's something that we would also like to quantify, specifically the carbon flux rates associated with POC. And then on the left, you have an image that shows vertical migration. And we are particularly interested in biologically transported carbon and the quantification of that. This is an area where there are significant unknowns, and very little is known about the macronecton and how they influence the biological carbon pump in the open ocean. So we see this as an opportunity to really do some fundamental work, developing new sensor technology to try to quantify how much these organisms impact the carbon cycle at sea. Next slide, please. So to that effect, this is a table of parameters that we feel are in scope for the Sea CO2 program. You'll see that some of them are inorganic, some are very specific, for example, pH or PCO2. Some are quite vague, sort of dissolved organic carbon. I mean, that's a category that could involve thousands of different types of molecules, biologically ingested carbon. But we consider all of these to be critically important in estimating the efficacy of CDR techniques. You'll see in the middle, there's a column that shows the state-of-the-art accuracy, and we've done our best to ascertain what the state-of-the-art is for each of the parameters. And these will become performance metrics for new sensors that are developed today. You have to achieve state-of-the-art accuracy, but do it in a volumetric manner. Next slide, please. So roughly speaking, we're trying to enable scaled CDR by economically decreasing the error between modeled and observed ocean carbon flux estimates. So in a nutshell, on the left, there's an image representing data collection. On the right, you have a model of CDR, and we're basically trying to correlate the two and reduce the RMS error. And that's the goal of the program in a nutshell. Next slide, please. We want to do that through creating comprehensive, scalable observation methods. Use those to verify models that show a path to bounding, to sufficiently bounding unknowns. So we don't want to determine what the variables actually are, although that would be nice. A more realistic thing to do would be just to bound the error bars. How much do we not know, or how do we make the unknowns known so we know what we don't know? Next slide, please. So thinking about sensing capability in the ocean for carbon parameters today, there are a variety of solutions available, and we've just plotted them on a time versus space logarithmic scale here, where the horizontal axis is time in a log scale, and then the vertical axis is spatial scale, also logarithmic. And while we have all of these technologies, they all have limitations. So for example, a sediment core gets you an incredibly detailed record of carbon sedimentation in a small area. And even 10 meters away, you may have quite a different record there. Conversely, you have a much better spatial capability with a mobile sensor platform, like an autonomous underwater vehicle, but only until the batteries run out. Even if you had a network of those types of systems, the cost would be prohibitive. The next slide, please. So we think that MCDR processes occur in time and spatial scales of roughly this area, so in the middle, and you can see that there's substantial white space there to innovate and develop sensors that have capability in the time scales and spatial scales that we need. Next slide, please. So the goal here is to move from today's paradigm of chemical-based sensors that may require reagents, direct collection at specific points in the ocean, and then detailed analysis of direct water samples through a wet chemistry assay, to this idea of sensors that are able to quantify these chemical oceanographic parameters in water volumes that are not coincident with the sensor. So electromagnetic, optical, or acoustical methods, wave-based methods that could sense volumes. And once we're at this point where we have volumetric sensing capability, we would expect a very large quantity of data to come through. And that data can finally be used to be applied to modern model generation techniques or learning artificial intelligence models that will create this transformative paradigm in terms of far more accurate models that are data driven in a way that replicates what has been done with weather forecasting, for example, over the last few decades. Next slide, please. So in terms of sensors, we need to perform a paradigm shift. Today, the state of the art involves sensors like the CO2 Pro on the top right there, a very accurate PCO2 system that brings in a volume of water, performs infrared spectroscopy on it. It takes a couple of minutes, then ejects that sample and brings in a new one. Now that's a very accurate system, but it's going to be very difficult to sample cubic kilometers of water with something like that. So going from this paradigm of sensors that look inward to something that looks outwards. We also want sensors that are inexpensive, reliable, they're able to exist in the ocean for long periods of time without undue maintenance. Next slide, please. So we have a few ideas here that we're sharing with folks just to get people thinking about what we could do. So on the right, on the left side, there is a montage of the state of the art. So we have an SVET sensor. It's a modern pH sensor that is a point receiver, very accurate. There has been a lot of work in understanding the calibration and operation of that kind of sensor at one point. But sensing a very large volume with something like this will be quite challenging. We have satellite surface remote sensing that offers a comprehensive scaled approach to quantifying surface properties of seawater only down to the first optical depth. And as a lot of carbon sequestration in the ocean involves the sinking of carbon, we need to track that carbon beyond the first optical depth. We have an example of a drifter, a minion. This is something that was developed by Melissa Omand at University of Rhode Island. This is an isopycnal drifter that looks at particulate organic carbon. Something like this could work, but we have to think about scaling here and persistence as well. This concept could we could improve the particulate organic sensing concepts that we have today by perhaps looking at things in a more volumetric manner rather than looking for things to settle on a glass plate. So on the right, there are a few potential transformative approaches. Firstly, we have this optical fiber concept. This isn't a new concept, but we haven't seen it demonstrated in real life yet. Distributed optical fibers are used for temperature and vibration measurements today in the ocean. But if you were to coat a fiber with a chemical coating that may mechanically respond to changes in the concentration of a chemical in seawater, you can couple that with a Bragg grating printed along the fiber, and any mechanical deformation due to that coating, say swelling because of a reduction in pH, you would then be able to optically sense this chemical parameter over kilometer scale ranges. There are a couple of plots there that show the relationship between boric acid and the boric acid and borate equilibrium reaction in seawater with chemical relaxation and absorption of acoustic energy. So as the ocean becomes more acidic, it is going to become more echoey in the 500 hertz to 1 kilohertz band. And if you are able to remove all of the other coefficients of attenuation to an acoustic signal, you could potentially ascertain what the pH is in a volumetric manner. This is something that, again, has been theorized, but hasn't really been demonstrated in practice at the scales that we find of interest. There are, of course, a large range of optical and hyperspectral approaches to quantify seawater and particulates. And another interesting concept that we're interested in, although we haven't found much in terms of literature on, is the electromagnetic sensing of seawater properties. This is something that is almost a lost art in ocean sensing. And we're really interested in talking to folks who may have ideas regarding how we could sense seawater properties, potentially biological activity, potentially seafloor properties very close to the surface of the seafloor using electromagnetic methods. Next slide, please. Here are a couple of ideas from the photonics and optics world. So on the right, there's a stylized image of something called a dual comb frequency laser. This is a system which provides an incredibly broadband coherent light source and can be used to conduct spectroscopy in air over several miles in range. There's an ARPA-E project called Monitor that pioneered the use of this type of system to monitor methane emissions in air. This type of system could be used underwater, either looking at backscatter from particles or absorption through transmission in seawater. On the left, there are some high-level figures from a program called Modular Optical Aperture Building Blocks, or MOAB. This is a DARPA program that sought to create solid-state LiDARs, and a solid-state optical phased array like a LiDAR, but perhaps combined with some spectroscopic system, would be really valuable in water because you wouldn't need a spinning device. You could encase the hardware in something that's much more pressure resilient and potentially much less expensive, while at the same time offering really superior spatial survey capability. Next slide, please. Last slide about concepts involves an acoustic one. So on the left, you can see there's an ADCP, which is a commonly available acoustic Doppler current profiler. These things use Doppler and backscatter from water particles to determine water movement at very fine scales. In this case, there's a representative plot in the middle there that shows the structure of turbulence obtained by an ADCP at operating about 2 megahertz. So these systems look at Doppler and water particle movement to ascertain water movement, water or shear, but there's some information there that is not used. For example, the phase changes due to impedance differences in water, attenuation, etc., can be used some other acoustic parameters that inadvertently come back to the receiver to try to gauge the chemical properties of seawater, or at least material properties of particles in the water. And to do this, one may need a fairly significant phased array, like the one on the right. Because we're looking at very high frequencies, the elements would need to be very small. But in the MEMS world, the microelectronic mechanical systems world, folks have been building these very large arrays of tiny transducers for a long time. So could these technologies be combined to create some sort of acoustic method of characterizing water properties? Next slide, please. So overall, in terms of the goals for the sensing component of this program, imagine a data set like the one on the left that's a satellite-derived image of chlorophyll A. But getting one of those without using a satellite, right? That's the goal. And another way to put that is, look at the picture on the right. There's an image of a NOAA ship with a multi-beam sonar swath underneath it. Imagine doing that, but rather than collecting acoustic data, you collect data about the carbon content of that water. I'm not saying that this is possible, but this is the dream that we have, the thing that we want to achieve with CCO2. Next slide, please. So just quickly I want to speak a little bit about the models component of CCO2. We think that mature MRV will be conducted through the modeling of real CDR approaches and a few validation measurements once the models are mature. I just want to give a shout out to one of our summer interns, Victoria Boatwright, who helped us with the program development this summer. So this was her thing, to look at the models. So we see a precedent here in the improvement of weather forecasts. So imagine a situation where you had this notional volumetric sensor producing a very large quantity of data that would then result in something that happens similar to what happened with the increase in accuracy of weather forecasting around the year 2000. So there's a plot on the right there that shows historical skill improvements from the European Center for Medium Range Weather Forecasting. And the time is on the horizontal axis, it's about 30 years, and the vertical axis represents the accuracy of model parameters. And you can see that those colors represent these different parameters. And at around the year 2000, that's somewhere in the middle of that plot, the variability decreased and the accuracy also increased substantially. And there were major improvements around that time due to the availability of new availability of digital satellite data, and then the consequent improvement in models there. We want to replicate that kind of increase in accuracy in undersea carbon flux sensing. So next slide, please. What we'd also like to do is, once we have this improved modeling capability, we want to try to communicate results to groups that perhaps aren't necessarily in the modeling, the scientific modeling community. So thinking about carbon markets and carbon registries, like the ones at the bottom of the slide, Vera, Carbon Plan, Nori is a carbon marketplace. We want to try and make these model outputs translatable to financial consequences for a CDR company, and these will lead to a data-driven carbon accounting framework, which is going to be, something that's a lot more robust than a qualification-driven framework that we have at the moment, and it's going to lead to a lot more certainty and value in carbon credits. Next slide, please. So just want to speak quickly about the tentative metrics for this program. ARPA-E defines its programs via its metrics. It sets a very high bar, and folks try to aim for them. So the first metric is about volumetric capability. We want to develop a sensing approach where, when the sensing approach is scaled to a gigaton scale, so the sensing approach is sized appropriate for a CDR approach that's capable of sequestering about 1 gigaton of CO2 per year. We feel that those sensors are going to need to survey about 150 cubic kilometers of seawater per hour. And that's new seawater, it's not the same volume. So any sensors developed under this program are going to need to be able to scale, hypothetically, to that sort of rate. We want them to be about as accurate as today's state-of-the-art sensors. The size, weight, and power need to be suitable for one of today's data collection platforms. So the sensors have to fit in an autonomous underwater vehicle or a mooring or something similar. The sensors must endure. So one of the big costs associated with ocean data collection is sending people to sea for switching batteries or performing repairs. So we want to try to minimize those costs. And then the modeling component of this program, we'd like to achieve modeling accuracy with historical data equivalent to what is state-of-the-art today, before the specific application of those models to simulating CDR events. Next slide, please. So we think that this program is going to run as follows. There'll be 2 technical areas, and for perhaps the first 18 months, the sensor folks will work on sensor development in a lab. Modeling folks will work on development of models and then testing via historical data. After that first phase, then the 2 technical areas would work more closely together. As sensors are matured and increasingly marinized, the specifications of the sensors would be communicated to the modeling teams, who would then perform what's known as an OSSI, or observation system simulation experiment, to see how much more accurate we would be in performing MRV with this new sensor technology, and therefore how much more valuable would the sensor technology be. At the end, we would like a sea trial that is as realistic as we can get for the sensors, and for the models, we would like to create this data-driven accounting framework and a forward-looking techno-economic analysis. So next slide, please. This hypothetical Gantt chart shows roughly the same thing. We think in phase 1, we'll have a lot of lab-based development, but in phase 2, there's going to be a lot more integration between the 2 technical areas, and then a set of increasingly realistic ocean tests. Next slide, please. Right, and I'd like now to hand off to my tech to market advisor, Dan Rogers.
Yeah, thanks, Simon. Can you hear me okay? Great. Yeah, so thank you everyone for joining the webinar today, and especially thank you to the folks at Ocean Visions for organizing the webinar. So I wanted to touch upon what our thoughts are in terms of the technology to market or commercialization aspect of this CCO2 program. And I just want to start off by sharing that the metrics by which we judge our success internally as an agency are very impact and commercialization focused. And those include the number of companies or startups started out of project teams that we've funded, the number of patents and licenses issued by our teams, as well as the amount of private follow-on investment that those teams receive to continue their commercialization efforts. So we're very much focused on, again, bringing our technology to market. And we have a saying within ARPA-E, and it's, if it works, will it matter? And so if you find yourself on a team that's proposing or submitting a proposal for this program, from the beginning, you'll need to think about what is your technology to market plan. And although we're talking about very hypothetical technologies at this point, and Simon even acknowledged that there's some approaches that we're not even sure are possible, even so, you need to be thinking from the very beginning, how can we help bring these technologies to market and make sure they have impact? And so for this particular program, we see this tech to market roadmap happening in 3 distinct phases. The first is the near-term need to develop new sensing capabilities just to prove the scientific and technical efficacy of the various marine CDR approaches that Simon has discussed. In the medium term, but still within the lifetime of this program, there are several steps that we're hoping our program can help advance in parallel to each other to help accelerate the adoption of a marine CDR industry overall. And those include working with carbon registries to develop new carbon market protocols and methodologies. And I'll discuss that more in a bit. It also includes working with state and federal regulatory bodies to help inform the drafting of regulatory frameworks. As of now, permitting and issues like that are quite uncertain, and it's not sure what the processes are going to look like for that at this point. However, we do hope that the data and information that we produce from this program can help inform the drafting of those regulations. And finally, we see a lot of application for new marine carbon sensing technologies in ocean observing, and we plan to coordinate closely with ocean observing systems globally, nationally, and regionally to help integrate new transformational carbon sensing technologies into existing infrastructure. And finally, in the long term, of course, the high growth economic potential and the true, high value pathway for these new types of technologies will be in carbon markets. And because we're primarily US focused at this point, we're focusing primarily on the voluntary carbon market, though of course, these technologies could also be useful in future and existing and potential mandatory carbon markets. So I just want to start with that kind of long-term goal that I mentioned. And if you're unfamiliar with the voluntary carbon market, which I'm sure many of you here are, but if you are not, it is a market that is experiencing tremendous growth right now. And in fact, you can see that the overall market trade value reached 1.4 billion in May of 2022, after having just exceeded 1 billion in September of 2021. And one estimate by McKinsey estimates that the voluntary carbon market may be worth anywhere between $30 and $50 billion by 2030. So we're anticipating tremendous growth in the voluntary market in this decade. A lot of this growth and demand is driven by corporate pledges for net zero or negative emissions in their operations. And we see that demand continuing to increase. Now, I will note that in the existing market, the vast majority of carbon credits traded are offset-based or mitigation-based, and only 7% or so are removal-based. However, one estimate that we saw showed that more than half of the credits traded by 2030 may be removal-based, and that includes several different types of approaches, including direct air capture, but could also include nature-based solutions, as well as the marine CDR approaches that we've been discussing. Again, I just want to briefly touch upon the mandatory market. Although we're focused on US markets, there's no certain future for a nationalized mandatory market in the US. However, we're starting to see these individual state and regional consortiums of states form their own mandatory markets. So these are also potential avenues that these new MRV technologies could serve. And I just want to highlight that globally, if you look at the graph on the left, you'll see that about a quarter of all global emissions are covered by some kind of carbon price.
Dan, I think you've gone on mute.
sorry about that. I'm not sure what, are you able to hear me? Great.
Yes.
Okay, sorry about that. I'll just want to point your attention to the graph on the left, which shows that about a quarter of global emissions are covered by carbon pricing instruments. And these are primarily, cap and trade systems as well as carbon tax systems. But you can see that, globally, there's an enormous market potential here that these MRV technologies could help to support value in. So whether you're talking about voluntary markets or mandatory markets or just the scientific and technical efficacy, there are certain variables that we need to look at in order to validate the usefulness of these types of carbon removals and ensure that they're high quality. So these variables include measurability, verifiability, durability, or permanence, as well as assessing additionality from natural baselines. And so we see MRV technology developed through this ARPA-E program as validating and supporting the measurement of these variables. Again, many of you are probably familiar with the entities in the voluntary carbon market, but if you're not, I just wanted to give you a high-level overview and especially point your attention to the entities on the right, because these are the types of groups that you may be working with if you're on a project team under this ARPA-E program. Carbon registries include groups like Gold Standard, BERA, American Carbon Registry, and Climate Action Reserve, which are some of the largest carbon registries in the US. And these are the groups that actually issue the carbon credits, as well as house the methodologies and protocols that are individualized to specific CDR project types. Project developers are the companies actually conducting the CDR activities. And these are the groups that are largely responsible for the planning and costs of MRV. And so we see project developers as being a primary customer of any MRV technologies developed under this program. And finally, I just wanted to highlight that the final step in a carbon registry actually issuing carbon credits is a desk audit by independent quality enablers, also called VVBs, or validation and verification bodies. And these are groups that are vetted by the carbon registries and who do usually an annual review of the removals that project developers are reporting. So these are the types of bodies that you may be expecting to interact with as an ARPA-E team under CCO2. Carbon registries, as I mentioned, house these protocols or methodologies for specific CDR project types. And these methodologies are incredibly robust documents that can be hundreds of pages of long, but describe how project boundaries are set, how the baselines are set, how you assessed additionality, and overall quantified the real benefits of the greenhouse gas or carbon emissions removed. These documents can be costly to develop, can be up to hundreds of thousands of dollars in labor time, as well as take anywhere from 9 months to 2 years to develop and get instituted. So in order to help accelerate adoption of marine CDR as an industry, we're hoping that, again, our project teams can coordinate with carbon registries and help develop foundational frameworks from which future project developers can author full protocols or methodologies. So again, we don't expect our teams to develop a full methodology, but we hope that we can use the data information produced by this program to help inform foundational frameworks from which future methodologies can be authored. Shifting gears a little bit, I just want to point your attention primarily to that bolded middle column. So these values are rough interpretations from our understanding of the National Academy's report that Simon discussed. And this was an exercise in basically trying to better understand what are the scales, the spatial and volumetric and temporal scales for which MRV will need to be conducted for the various approaches to marine CDR. And again, these are not hard and fast numbers. These are our interpretations from examples in this report. But you can see on average, we're looking at tens of thousands, hundreds of thousands, in some cases, millions of square kilometers just to reach 100 megatons of CO2 removal per year. So enormous areas and volumes that need to be sensed. And so long-term, our vision is that, in order to support economic MRV at these scales, we'll need scalable sensing technology, trusted and verified models, as well as durable and connected platforms. we think all three of these are important pillars to supporting that economic MRV. However, in order to maximize our impact with the funding that we have available through this program, we're going to focus on those first two pillars, the scalable sensing tech and the trusted models. Though we hope to perhaps support our project teams in developing full MRV solutions that might include novel platforms in the future. But again, this program is focused on those first two columns. Obviously, another industry that has similar challenges is an ocean observing. And so we hope to, again, closely coordinate this program with ocean observing systems, both nationally and regionally, and also locally. And if we're able to produce some low-cost, transformational new type of marine carbon sensor, we want to work with these organizations to help integrate these new sensors into existing ocean observing infrastructure. And this is going to also serve the marine CDR industry, because by having better understandings of the natural baselines in the ocean at these scales, we're going to be able to know what to measure future engineered marine CDR processes from. So we see this as being valuable to government and academic research purposes, but also for marine CDR as an industry overall. And again, I'll wrap up by just describing how we see potential market entry pathways for the teams that are funded under this project. We're trying not to be too prescriptive, because it's ultimately really going to depend on the modularity of the MRV solutions that are developed. But we could certainly see some teams forming manufacturing partnerships and doing direct sales of MRV devices. We could see novel sensor designs being licensed out to larger and existing oceanographic sensing manufacturers. Though it's possible that some teams may wish to create an end-to-end sensing and modeling MRV solution that a project developer could directly contract in order to get that MRV data. So again, trying not to be too prescriptive, but again, if you end up on a team that's submitting a proposal, please keep in mind, if it works, will it matter? And with that, I'm going to pass it back to Simon to wrap up. Thank you.
Thanks, Dan. So what now? If you have ideas for how you think we could transform our MRV capabilities for marine carbon dioxide removal, I ask that you potentially develop those ideas to address the metrics that we've issued here at this in this presentation, with an emphasis on volumetrics, with an emphasis on reliability, etc. This is going to be an interdisciplinary challenge. So if you are, say, a sensor developer, consider partnering with an oceanographic institution or an ocean engineering firm. We will also need folks to interpret the data that the sensors produce, so marine biologists, chemical oceanographers, and the like. If you're a modeler, consider working with a carbon registry. And again, we probably need input from scientists such as marine biologists and chemical oceanographers, as well as potentially physical oceanographers who really understand these ocean systems. See our teaming list announcement, which is on the ARPA-E funding opportunities announcement website. That's down the bottom of this slide. You can also Google it in a very straightforward way. Inquire about our industry day in late January, where we're running a proposers day for the purposes of teaming. And that's going to happen before the funding opportunity announcement goes live. We're hoping for that to happen sometime in the next 1 to 2 months, but we can't be sure until it goes live. So next slide, please. With that, thank you very much for listening. We're always looking for ideas and people who may change what is possible. Please contact us, myself or Dan Rogers. Our email addresses are shown on the slide. Thank you so much.
Well, thank you, Dan, and thank you, Simon. That was a really wonderful presentation. This now concludes the presentation part of today's webinar, and we're going to move into Q&A. So if you have questions that emerged from this presentation, please register them in the chat, and I'll try to feed them to Dan and Simon. I want to start, though, while you're all stewing on your questions, by asking Dan and Simon about the degree to which this program will or will not coordinate with other federal entities and other federal activities in the marine CDR space.
So we are attempting to coordinate with other agencies. The government has many different hands, and it's sometimes challenged to get them to talk to each other. But for example, you may be aware of the National Oceanographic Partnership Program has a current funding call that specifically references this upcoming ARPA-E program. And the idea there is to coordinate with NOAA, I think is the lead agency, to work on developing sensing technology that could validate the efficacy of CDR implementations that are performed under that NOP. And so put it at a very high level, and if they research and develop the CDR approaches, we would support by researching, developing, and deploying MRV technology hopefully at the same time. There are other potential calls on the horizon, funding calls, and we're working with folks at the Department of Energy, Office of Fossil Energy and Carbon Management is one example, to try to coordinate and collaborate where possible.
Thanks, Simon. We had a question during the presentation from Galen McKinley, which was fundamentally about this question about additionality. You know, there's a really substantial natural ocean carbon sink, and fundamentally marine CDR technologies need to uptake additional carbon dioxide beyond that level of natural carbon sink capacity. And so how will this program address the challenges around additionality?
So we see the only the only way to really perform additionality is through the quantification of additionality is through modeling parallel processes. So if we are able to produce models of sufficient accuracy, we could run two parallel scenarios of a given region. We use the same initial conditions. One model has the addition of carbon through some CDR process, one does not. And the two outputs can then be compared. Of course, the outputs are not hard and fast. I mean, there are probabilities associated with everything, and the probabilities will probably, the PDFs will probably overlap, right? So there we need to consider what the level of certainty is. So there's a sophisticated data analysis and sort of conclusion drawing process that we will probably need to engage in. This is something that we would like to work closely with carbon registries on, because there are direct implications regarding the value as to the certainty of estimates of additionality.
Thanks, Simon. Moving on, we had another question from Lipsa Nag that I'll read in just a second, but I want to remind folks that we want to try to make this as interactive as possible. So please, if you have questions, to register them in the chat. And now moving back to Lipsa's question, she was asking about how much future sensor technology will depend on miniaturizing current sensors.
Well, this is a really interesting question because it touches on a broad trade-off here. And with miniaturization, there are also implications for cost and economies of scale and productionization, right? If you had one exotic, extremely capable sensor, we can afford it to be very expensive because it would enable the survey of a significant volume of water. Let's say it was very capable and you could survey cubic kilometers per hour. Great. But more realistically, these new sensor designs are probably going to be limited in range. And so you would need more of these things per unit of seawater volume, which would mean that for a given budget, each unit would have to be less expensive. So just how much less expensive? Well, it's somewhat inversely proportional to the range capability. So there's a trade-off there. So if you could miniaturize something that is, let's say, even a point receiver and reduce its cost, it could potentially be competitive if there was a feasible method towards scaling. So I'm assuming that there's a connection here between miniaturization, cost, and then economies of scale. But as we've seen with terrestrial sensors, let's say the sensors in drones, et cetera, that has been the case.
We had another question about data assimilation. In the slide on weather forecasting, you were showing the improvements in uncertainty and also accuracy around these key parameters for weather forecasting models. And implicit in that is this fundamental idea about data assimilative models, right? Models that incorporate large streams of data. In this case, you were talking about weather satellites and feed them into models to improve model accuracy. And so the question from David Anderson is, do you see data assimilation playing a similar role in MRV? And perhaps you could elaborate a little bit more on that about how you see data assimilation playing a big role.
Well, it's going to be essential, but in terms of this program, it's going to be a little challenging because this is primarily a sensor development program with a significant models component added onto it. The sensors have to come before the models, and it does take some time to develop new sensor processes. I mean, first, you could have a basic demonstration on a bench top, then how long until that system can be fielded in the ocean, right? It takes some time. Nominally, this program is going to be about 3 years in length. So if possible, we would love for models to be developed in parallel with data assimilation capabilities that rely upon data from new sensors, but we're not assuming that the new sensors will be available in time. So it's a nice to have, not a must have, but moving forward post CCO2, we would expect this to be the case. So everybody would need to prepare for the eventuality of large scale data assimilation from these sensors to like models that are regularly updated.
I think we have time for about one more question, which comes from Alice Letcher. A practical question: how many project teams does ARPA-E foresee funding?
Well, I can only talk about a prospective budget of $30 to $50 million, and typically ARPA-E projects per team, the average amount awarded is roughly the $3 to $5 million range. That said, I think that the funding opportunity announcement might say something like, we're looking for proposals from the region of $500,000 to $15 million, right? We'll keep it quite open, and we will evaluate the proposals in order of competitiveness. And I mean, we would like to support as many different potentially transformative and unique ideas as possible.
Great. I want to give each of you a chance to impart your last words of wisdom to the audience here. So maybe let's start with Dan first.
Sure. And as we wrap up, just thank you again, David, and everyone at Ocean Visions for this opportunity. We're really excited about this upcoming program. And again, I just want to point out that we've had many people come up to us and ask, hey, I'm a research scientist. I work in an academic lab. I haven't thought about commercialization or technology to market. And I just want to point out that as an agency, about half of the teams that ARPA-E funds are academic labs. And I believe from there, about 20 to 25% are small companies and startups. 5 to 10% are large businesses with research arms, and 3 to 5% or so are philanthropies. So a very broad range of different applicants and performers at ARPA-E. But I just want to share that we are here to help coach toward commercialization. We're not here to just adjudicate milestones and contracts. We're here to help provide the technical and the commercialization expertise to help make sure that any technologies developed under this program can have impact. So if you're concerned about that aspect of your proposal, you should find a partner who has that expertise and who can bring that to the table and work with you throughout the lifetime of your project. So with that, thank you again. And Simon, I'll pass it over to you to wrap up.
Thanks, Dan. Well, we're very excited to launch this program at ARPA-E. It's part of a recent foray into emissions mitigation and especially emissions abatement for historical emissions. If you recall, for a while at the beginning of the Biden administration, there was some talk of ARPA-C, which didn't happen. But unofficially, I mean, I feel like this agency is taking on some of that, the research directives associated with that. We're very excited about trying to kickstart a significant negative emissions economy, a maritime economy, and we look forward to supporting innovations over the next few years that can potentially make that possible within the decadal timeframe. So if you have ideas, please get in touch with us. And of course, if you'd like to attend our teaming day, I think that's in late January. It's an in-person event in DC, the purpose of which is so that potential PIs or potential collaborators could get up on stage, briefly speak about what part they would like to play in a team, and then network. Please get in touch with us. Thank you very much. And thank you to Ocean Visions for hosting us today.
Well, thanks, Simon, and thanks, Dan. This brings us to the top of the hour, and I just wanted to let you all know that we have recorded this event, and we will make this recording available to all of the registrants within the next week or so. So keep an eye out via email for that link. So thank you very much for your attendance. Thank you very much for your interest, and thank you very much for your participation. And I look forward to seeing you all at the next Ocean Visions webinar. Have a good day.
Thank you.